Guys, welcome to this new video. So this is going to be the rigid body mechanics question from the May 23 time zone 1 paper 3. So here we're given a uniform rod of length 1.2 meters on a horizontal surface. It's at rest. The rod is pivoted at its center so that it can rotate around the pivot. And then we have some particles striking one of the ends of it. This has a mass of 0.2 kilograms and it's moving at 12 meters per second and it sticks to the rod. So the moment of inertia of the rod before was 0.18 kilograms meter squared, and we need to show that the moment of inertia of the rod particle system is about 0.25 kilograms times meter squared. So we need to remember that moment of inertia is just the sum of mr squared. So what that means is that if we have some axis, so for example this axis over here, and we have some particle on either sides of the axis, then we have some distance from the axis to the particle. This will be r, and this particle has a mass of m. And so if we want to calculate the moment of inertia of something, we need to take the mass of a point mass, as this particle can be considered as just one point. We need to consider its mass and multiply it by the distance squared from the axis. And this is how we would need to calculate the moment of inertia of any object. So for example, if we would want to calculate the moment of inertia of this rod, then we would need to take every single point in this rod, consider its mass, consider its distance from the axis, do r squared times m for every single point and add them all up. So that we could do with an integral, but in IB we don't need to learn how to do this, but that is how it would need to be done. So just sum every single point's mass times radius squared, and then we would find the moment of inertia of 0.18, but IB already gave this to us. But when we only need to do this for like 1 or 2 point masses, not for like a lot in a rod, then we can just do this by hand through this simple mass sum formula. We can just add them up. So we know that before our moment of inertia was 0.18, and to this we just need to add the moment of inertia of this particle, as it's just like it's like if there would be another particle over here. Since we were already summing every particle here, we just need to add this one as well. It's just like another point mass on the rod, so nothing special. And then the moment of inertia of that will just be its mass, so 0.2 times the radius squared, so 0.6 squared. Make sure not to take this 1.2, as we just need the distance from the axis to the point mass, not the full distance of the rod. And then if we do this, we get 0.252 kilograms meter squared, like this. And then we need to show that the angular speed of the system immediately after the collision is about 5.7 radians per second. Well, here we need to consider a bit of angular momentum conservation. So the angular momentum before and the angular momentum after the collision must remain the same, as angular momentum is always conserved. It's just like we had linear momentum in regular mechanics, where it was m times v, that's always conserved. While here, linear angular momentum is symbolized with L, and is just the moment of inertia times the angular speed. So, and we need to consider this before and after, and we know that they're the same. So we need to calculate the initial angular momentum. And well, at the start, only the particle was moving, right? The rod was stationary, so the rod had no angular momentum. But the particle did have some angular momentum about this axis. And how we can calculate that is with this formula. So first we need to calculate its angular speed. And well, how we can do that is we know that angular speed, well, we know that v is equal to angular speed times radius. This isn't necessarily in this topic. I think it might be in some waves topics or some circular motion topics, but it's important to remember this formula. So we see that angular speed is just the velocity over the radius from the axis. And well, we know that the moment of inertia is just going to be 0.2 times 0.6 squared. So this is the moment of inertia, and then our angular speed will be v over r. So 12 is linear speed divided by the distance from the axis, so that's going to be 0.6 again. And then if we do this, we get that this is 1.44 joule seconds. Although it's probably not, you don't need to write these units, I think, in between. Just make sure you write the final units. These are just like some in-between calculations, but anyways, it's important to remember what units you're working in so you don't start mixing units. All right, so now we have the L initial, and now we need the L final. Well, the final momentum will just be the total moment of inertia of the system and the final angular speed. So our total moment of inertia is just what we calculated already, so 0.252, and this angular speed that we don't know. But we know that these two are going to be equal, so we can solve for the angular speed. So 1.44 divided by 0.252. So that will give us 5.71 radians per second, which is approximately 5.7 radians per second. Now we need to calculate the energy that was lost. So at the start we had some kinetic energy, and at the end we also had some kinetic energy, and we kind of have to see the difference between these two. So, well, at the start we only had like normal kinetic energy, and at the end we had like rotational kinetic energy. So we're going to have to calculate the difference between these two. So at the start we had only just like the 1/2 mv squared type of kinetic energy. So 1/2 times the mass of the particle, 0.2 times its speed. That will give us well, we don't really need to calculate it, as if we just write up the E kinetic final, then we can just subtract them, and then we can plug everything into our calculator as one calculation. And then we don't need to round anything. It will be as precise as possible. And at the end, then we're going to have to use the formula that for rotational motion, kinetic energy is 1/2 moment of inertia times angular speed squared. And well, we know our final moment of inertia, 252, and then times by our final speed squared, so 5.71 squared. And if we do this initial minus E kinetic final, then that will be our lost. So that's our lost energy, and this is going to be just 10.3 joules. So this is how much energy that we lost due to the collision. And then we are told that there is a frictional torque of magnitude 0.152 Newton meter that acts on the system just after it begins to rotate. We need to calculate the angular deceleration of the rod. Well, torque is kind of like net force in our mechanics syllabus. So our net torque we know is moment of inertia times the angular acceleration. This has a parallel to F net equals ma from mechanics. So, well, we know our torque, we know our moment of inertia, so our deceleration will just be net divided by moment of inertia. And so that will be 0.152 divided by 0.252. So that's 0.603 radians per second squared. And then if we want, we can calculate, we can also put in a negative sign over here, although that isn't necessarily required for the mark, as we were asked to calculate deceleration, so we can just say that this is our deceleration, but if you want, you can also put a negative sign. And then we need to calculate the number of revolutions made by the rod until it stops rotating. So here we're going to have to use some of the Suvat equations made for rotational motion. They're pretty much the same equations, just different symbols. So we have this formula that V final squared is equal to V initial squared, well, omega, not V, omega final and omega initial, plus 2 times the acceleration times the change in angle. So this is the V squared is equal to U squared plus 2AS from mechanics, whereas we just have the appropriate symbols here. And well, we know our final speed is 0. We know that, yeah, then we can just rearrange the formula. So we will have that omega initial squared is equal to 2 alpha times delta theta. Both sides would have a negative sign because our acceleration is negative, and since I brought the initial angular speed to the left, that would also be negative, but I already just canceled them out. And then we can solve for the delta theta. That will just be omega initial squared divided by 2 times the acceleration. So 5.71 divided by 2 times 0.603. So that will give us 27 radians. But that is not the number of revolutions. We are told that it covers 27 radians as it stops. And well, we know that 1 radian is a 2 pi. So that's just how we define it. So if it goes 27 radians, and well, 2 pi is just 1 rotation, or 1 revolution. It goes completely around 1 times in 2 pi. 2 pi is just 360 degrees. So 27 divided by 2 pi will give us 4.3. So it will complete 4 revolutions and like a little bit less than a third. And that's our answer. And then in another situation, the rod is on a horizontal frictionless surface with no pivot. So you can think of it something like this. And then the particle is still coming and is still colliding with this rod. And we need to predict the motion of the rod. So, well, first of all, it's still going to rotate. So it's still going to rotate. And well, about where is it going to rotate? Well, it will rotate about its center of mass, as that's just how it likes to rotate. So around center of mass. And well, it's not only going to rotate, as we didn't pin it down here, so it's also going to move a little bit this way due to the impact force of the particle is going to slide also like downwards down the table. So it will, we could say, like the rod will move along a straight line. And if we want to be more precise, we can say that the center of mass will move along the straight line in a direction parallel to the initial speed. Well, not initial, but like the speed of the particle. And seeing this is a little bit tricky, as we haven't really learned, like, I think all the necessary knowledge for this in IB, or at least I don't think so. Maybe there is some parts in books that explain this, but if we think about it, our center of mass is over here. And well, since this is like a free body diagram, there's like some force over here due to the particle. We can push this force into here, into the center of mass of the rod. So this will show us that the rod will move this way. But if we reposition a force, we also need to create a torque for it, because this force has a torque around this point. So like if we want to replace this force, so this force I just deleted, with some force in the middle of the rod, we can delete this. So we can move the force over here. Forces we can just move anywhere we want, but if we move a force, then we also need to account for the torque that this force was producing around this axis. So we can move it here, and then there will be some torque over here, and then this will technically show us how it will move. So it will move in a straight line this way, but at the same time is going to rotate around that center of mass. Although this is probably a little bit hard to see just with knowledge from the IB, I would say. So this was the end of this rigid body mechanics question. I hope I was able to help your understanding, and see you in the next question.